All right, so here we go. XOR, XNOR, and binary adders. Okay. XOR and XNOR stands for exclusive or exclusive NOR. Okay. And these gates specifically can be used to create a full or half adder, okay, which is the most basic way to add binary bits together. Okay, this is really another one of those foundations of computing and computers. So how are we able to take binary information and combine them? Okay, we learned about choose complement and how to do the math on our own. And this is really more about then how on a physical level in the computer are we actually now doing this this math? Okay, it's one thing to talk about it theoretically, but it also has to physically be implemented, and this is how it's going to be done. Okay. So exclusive OR, okay, is basically if we took the OR truth table, but we said we're only going to take the ones that where we have one or the other. So we're not going to take the and situation, and we're not going to take the neither situation, but we're going to take only the or situations, only one or the other, but not both. Okay. If we do the Boolean, it's going to look like this, right? We can have not X and Y, or we could have X and not Y, okay? And as far as Boolean is concerned, we can simplify that by showing it in this way. So the little circle with the plus in the middle is the symbol for the exclusive OR, okay? So if you do come across this in some kind of Boolean scenario as well, you can substitute then this formula for that in there, and then you may be able to do some further breakdown for Boolean. Okay. Right, Jaden? Just make sure you're with me and not in Slovakia there somewhere. Okay. So similarly, we have XNOR here. Okay. Same concept. Okay. This would be the NOR gate, which remember was already an inversion of the OR gate. Except again, now we have the opposite where we're exclusively taking either both zeros or both ones, but not the one or the other. Okay, so exclusively not or is really the inversion of the XOR gate. Okay, again, Boolean wise, we've got it could be not X and not Y, or it could be X and Y. All right, and this would be again the consolidated version of it for Boolean. Okay, but it could be expanded back out for the purposes of doing reductions. Okay. So here we're going to basically do a little Boolean and break down. Okay. What we'll be able to see here, we don't see any exclusive or nor symbols in here, but we're going to get to a situation as we break this down where we're going to be able to substitute in an exclusive nor or exclusive or for some other combination of gates. What's that?
Is there a cheat sheet for memorize these?
No, there won't be another cheat sheet for this one. Okay. So here's essentially what the solution looks like. They were able to extract Z here, and we got this X not Y or not XY situation that can be substituted for the exclusive OR. Here they extracted not Y, and a similar concept, right? We've got not X, not Z, or X and Z, and that was able to be substituted in for the exclusive NOR gate. Okay. Down here, we can see the gate implementation. Okay, so we've got the exclusive OR, exclusive NOR, and then we've got the remaining AOI logic to complete the circuit. Okay. All right. We've done this to death and choose complement, so we get the basic concept of how to add and carry. Okay. And here we have two different types of adders. Basically, we have one that can take 2 bits in and can return a sum out or a carry out. Okay, so if you carry over to the next place, this would basically be the first. If we had a series of adders, the half adder would be the first. Okay.
What is the carry?
So basically, if we have a situation, Jaden, where we have 2 ones and we need to carry over to the next place in line, okay, and they're going to show a multi-bit implementation here in a second, but that's really what we're looking at. So, for the first column, though, here, where we only have the possibility of 2 bits coming in, there is no option for a carry because it's the first bit, okay, in order. That's where we would use the half adder, okay. the full adder here has the option for my A bit, my B bit, and a carry in from the previous adder, okay? So I could do a half adder to this one, or if we're going from a full adder to another full adder, then again, the C out could tie into the C in of the next, okay? Basically allows for the 2 bits putting in plus the carry from the previous place, okay? All right, this is some more specific information about how it functions. Okay, I don't think that's anything we need to worry about in particular. Okay, this is what the logic would look like for the half adder. So we have the exclusive OR gate and we have an AND gate. Okay, this makes sense, right? We need both A and B to be ones for there to be a carry out situation. Okay, and in here, if it was one or the other, then the sum would be 1, okay? And if they're both ones or both zeros, then either, if they're both ones, it's carrying out, and so the sum is 0 because we're carrying. If they're both zeros, then there was no addition taking place, and there's no sum and no carry.
Can the X is followed by the little like loop you do on the back?
Say that again?
There's a little like second loop on the back of the X.
Well, this would be, I'm not sure what you mean, the X.
Looks like exclusive Xnor X.
Oh, yeah, the loop on the front would be exclusive NOR. That's the second curve means that it's exclusive gate. Otherwise, it's the same design as the OR gate, but this has the double back. That's how you know it's an exclusive OR. All right, so here we've got the truth table for the full adder. You can see the K-map again. I'm not going to bore you with the proof of it here, okay, but know that it works, okay. Here again, okay, for the full adder with the sum in, okay, again. Let's not worry about it too much. You can see they worked it all out for you with a whole bunch of wacky substitution, okay. For you guys who got to the end, this was the answer to that conclusion question. This is how they do it with this, this wacky substitution here that I wouldn't expect you to think of on your own. Okay. All right, and here's the full adder circuit. Okay, so again, this accounts for 3 possible bits coming in, the A, the B, and the carry. In this case here, we need 2 of the exclusive OR gates to make that work. Okay. And then as well down here, we've got several AND gates to account for adding of the first and the third, first and the second, second and the third bits. Okay, any of those situations could cause a bit to be carried out, right? So basically, if A and B are ones, that would be a carry. If A and the C in are ones, that would be a carry. If B and C in are ones, also a carry. Okay, so any of those situations could work here for a bit to be moved over to the next column. Okay. All right, and this is just showing you, this is what the AOI implementation would look like. This is what it looks like basically with the XOR. So why do we need the XOR gates? Well, because there's a big time savings for total number of gates to implement them. Okay. MSI stands for medium scale integration, and that just means, okay, this is what the full package chip looks like. Instead of doing individual gates, this is the chip that you're going to be using in multisim to actually do the designs. If you were to breadboard this is what you would be using, okay? All right, and again, this is what it would look like. This would be the first one in line. So a half adder, a full, and a full would be the equivalent of doing this 4-bit binary addition or subtraction, okay? And again, really in multisim, okay, or if you were to breadboard, this is what the packaging would look like, okay? Here they've done it with all full adders except the very first bit here. They grounded out the carry because there should be no possible input for the first bit in line, okay? But the ones place carries to the twos place carries to the 4 carries to the 8th place, okay? And we could keep on going if need be. All right? And that's really the gist of it, okay? So, again, exclusive OR and NOR, really their sole purpose is for doing the binary addition here. And they're just going to get you introduced to wiring these and using these. Eventually, they have you hook it up to a 7-segment display, okay? And get that all functioning, all right? And again, be comfortable with this because you will see it again in our next unit when we move over to the programmable boards, you will be designing a counter and an adder that will display on 7 segment displays.